In this video, we are going to examine the solubility of ionic compounds. A compound is said to be soluble if, when you put it in a liquid, it totally dissolves in that liquid so that it disappears. An example of that would be sodium chloride or table salt. When you put it into water, it disappears or dissolves, so we say that it is soluble. A compound that is soluble in water is said to form an aqueous solution, and oftentimes we'll abbreviate that as AQ. Now, a compound is said to be insoluble if, when you put it in a liquid, it does not dissolve. An example of that would be silver chloride. If you put silver chloride in water, a solid crystal of silver chloride, it will just sink to the bottom and won't dissolve. Even though a very small amount of any solid will dissolve to some extent, generally insoluble compounds do not dissolve to any significant extent. So how can you tell if an ionic compound will be soluble in water or not? Well, the first thing we have to do is look at the chemical formula and identify the cation and the anion. Once we identify the cation and anion, we look at our solubility rules or guidelines for soluble and insoluble compounds. So let me go over the solubility rules with you very briefly, and I want you to take a little extra time and be familiar with them. Basically, what this tells us, this first table, is which compounds are soluble when put in water. So any compound that contains as a cation lithium, sodium, potassium, rubidium, or cesium, or ammonium, those will always be soluble. It doesn't matter what anion they're paired with. Any compound that contains the nitrate, acetate, or chlorate anion will always be soluble. Again, it doesn't matter what cation they're paired with. Compounds that contain chloride, bromide, or iodide anions will be soluble, except if the cation is silver, mercury 1, or lead. So if you had silver chloride, silver bromide, silver iodide, those compounds would not be soluble. Compounds that contain the sulfate ion are generally soluble. Again, there's a few exceptions. Silver, mercury, lead, calcium, strontium, or barium, when paired with sulfate, will form an insoluble ionic compound. Now this table looks at some rules for insoluble ionic compounds. Compounds that contain the carbonate, phosphate, chromate, or sulfide anions will be insoluble unless they're paired with the following cation: lithium, sodium, potassium, rubidium, cesium, or ammonium. And compounds that contain the hydroxide ion will generally be insoluble. And again, our exceptions there are our alkali metal cations in addition to barium. Now you may find some ionic compounds that don't match up with ions on the table. For example, magnesium oxide. Magnesium's not on this table, either table, neither are oxides. So if you find a compound composed of ions not found on either table, those compounds are considered to be insoluble. So take a look at the guidelines and use those to determine if each of the following ionic compounds will be soluble or insoluble in water. So pause the video and answer those questions. Okay, let's take a look at those. The first one, sodium carbonate. Any compound that contains sodium will be soluble. So that would be yes. Calcium chloride. We said that the chlorides, any compound containing the chloride anion will be soluble. So that would be yes. And again, silver chloride, that contains chloride, but silver was one of our exceptions, so that is insoluble. Barium sulfate, generally compounds containing the sulfate ion are soluble. However, barium was one of our exceptions, so that is insoluble. Ammonium sulfide, Most compounds containing the ammonium cation are soluble, so that would be soluble. Copper hydroxide. Hydroxides tend to be insoluble, so that is insoluble. Barium hydroxide. Again, hydroxides tend to be insoluble, but barium was one of our exceptions, so be sure you check those exceptions on the table. Calcium phosphate. Phosphates tend to be insoluble, and calcium is not an exception to that rule, so that compound is insoluble. Lead 2 nitrate. Compounds containing the nitrate anion are soluble, so that one would be soluble. And lead 2 chloride. Again, chlorides tend to be soluble, but lead was one of our exceptions, so that would be insoluble. So be sure you're familiar with those guidelines for soluble and insoluble ionic compounds. So let's take a closer look at solubility of ionic compounds. When you put an ionic compound in water and it dissolves, so it is soluble, the anions and cations, which are ionically bonded to each other, will separate and disperse throughout the water. And this process is called dissociation. Now remember, not all ionic compounds are soluble, so only soluble ionic compounds will dissociate. Insoluble ionic compounds will just sink to the bottom and will not dissociate. Furthermore, if you have an ionic compound that contains a polyatomic ion, when you put the ionic compound in water, the cations and anions will dissociate, but polyatomic ions do not further dissociate. The polyatomic ions will stay together as one ion. So how do ionic compounds dissociate in water? Well, let me show you a short video which kind of shows how the water interacts with the cations and anions and pulls them apart from one another in order to illustrate this dissociation process.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
So when we're examining the dissociation of ionic compounds in aqueous solution, we like to represent that using a balanced chemical equation. Let me show you some examples of those to illustrate what I'm talking about. Let's say we wanted to look at the dissociation of potassium iodide in water. This is a soluble compound, and so when you put potassium iodide in water, it dissociates or yields potassium ions and iodide ions. So 1 mole of potassium iodide will dissociate to give you 1 mole of potassium ions and 1 mole of iodide ions. So here you can kind of see it pictorially represented. Here's the potassium and iodide ionically bonded. When put into water, the ions dissociate from one another to form separate ions. If you put copper 2 sulfate in water, copper 2 sulfate, here's our chemical formula, in aqueous solution, it will dissociate to give you copper 2 ions and sulfate ions. So 1 mole of copper sulfate will dissociate to give you 1 mole of copper 2 ions and 1 mole of sulfate ions. Now here, appreciate that the copper and the sulfate dissociate from one another, but the sulfate ion does not further dissociate. As we mentioned before, the sulfate ion is a polyatomic ion. It will not break apart into sulfur and oxygen atoms. So remember, polyatomic ions, they dissociate from the cation, but they stay together as one unit. So let's look at potassium sulfate. If you put potassium sulfate in water, here's our chemical formula. 1 mole of potassium sulfate in aqueous solution will dissociate to give you 2 moles of potassium ions and 1 mole of sulfate ions, because potassium sulfate is composed of 1 sulfate ion and 2 potassium ions. So when these ions break apart, we end up with 2 potassium ions and 1 sulfate ion. All 3 of these ions are separate from each other and dispersed throughout the water. Now, one thing that you want to be very careful not to do when you're writing a dissociation equation for something like this, the 2 potassium ions we represent with a 2 coefficient. We do not write something like this, K2. This indicates that the 2 potassiums are bonded together with a subscript. So these 2 potassium ions are not bonded together. They separate from each other. So we would not want to write K2 with a subscript. We would write 2 potassium ions plus 1 sulfate ion. So let's take a minute and get a little more practice writing some dissociation equations. So for each of these ionic compounds, be sure it's soluble, and if it's soluble, write the dissociation equation. Be sure it's balanced, and be sure to include the state, AQ, after each of your compounds. So pause the video and give that a try. Okay, so let's take a look at this. Potassium hydroxide is soluble, and we get 1 potassium ion plus 1 hydroxide ion for every 1 mole of potassium hydroxide. Silver bromide is insoluble, so we can't write a dissociation equation because it doesn't dissociate. Calcium chloride, 1 mole of calcium chloride in water will give us 1 mole of calcium ions and 2 chloride ions. Again, 2 with a coefficient, not a Cl2 minus. That is not correct. Lead 2 nitrate dissociates to give us 1 mole of lead and 2 nitrate ions. Again, the polyatomic ions do not dissociate. They stay as 1 unit. Lead 2 sulfate is insoluble. You want to review the rules for solubility. And finally, aluminum sulfate. If we have 1 mole of aluminum sulfate, it dissociates or breaks apart into 2 moles of aluminum ions and 3 moles of sulfate ions. So we want to be sure we include the correct coefficient. Be sure your charges are correct. Be sure you have AQ to indicate that those ions are dissolved in water for each of these equations. So be sure you practice some of these and appreciate how these ionic compounds dissociate when put into water.